Swayam Prabha. Digital India. Educated India.
We have completed two sort of sections in this course. First one was on the protection basics and protection paradigms and algorithms. And the second one was on the numerical relaying um, aspects like sampling theorem, DFT, calculation of system frequency, though that part is now complete. So we will now move on to the last section, that is some advanced topics in which we will cover wide area monitoring systems or wide area measurement systems, including its components like PMUs, etc. And then we will end this course, but before that there is a small subsection left, which is unit protection, which we did not cover earlier. So at the absolute end of the course we will cover that in maybe 1 or 2 lectures. Unit protection means bus bar protection, transformer protection, generator protection, and then we will close this course. So this is in a sense the last part of the course or the last section of the course. So let's get started on wide area. We will cover the basics of wide area measurement systems, and then maybe a few minutes or maybe half the lecture or so we will maybe a couple of lectures later we will see integration with protection in what is known as WAMPAC, wide area monitoring, protection and control. But first we will look at only the wide area measurement systems in today's class and the next class. So to begin with, this is what we will cover in this lecture and maybe some part of next lecture. First one is why we need to go in for wide area measurement systems. We already have sort of wide area measurement systems in SCADA, which is the supervisory control and data acquisition systems, but there are certain limitations. We will look at that and then we will see why we need wide area measurement systems. Then what are the wide area measurement systems, what are the building blocks, then what are the measurement criteria for wide area measurement systems, what are the communication requirements, and some other components like once we cover PMUs there is also something known as a PDC or a phasor data concentrator. So we have a look at that and applications. All this of course we will not be able to cover in one lecture. So some part of applications and maybe some part of even PDC and other components we will spill over to the next lecture. So let's get started. So one of the motivations of going in for a PMU based system have been blackouts, not only in India, even worldwide. The New York blackouts of the 2000, that era prompted the US utilities to go in for installing PMUs in their system and then going in for WAMs. So also in India, we had a blackout in July 2012. So that is almost 11 and a half years ago, and this was quite severe. It happened back to back. It happened on 2 days. I think 30th of July and 31st of July in 2012. So this you can see there were a few PMUs in the system at that time. PMUs are phasor measurement units. What a PMU is, and I mean a brief logical block diagram of the PMU we will see in subsequent few slides. But there were a few PMUs in the system. They were installed in I think there were 4 or 5 PMUs, but also there were in IIT Bombay itself in one of our labs headed by Professor A.M. Kulkarni, there was indigenously developed a system known as Wide Area Frequency Monitoring System, WAFMS, and this was a system in which the measurement units were installed in labs at our domestic outlets. So, the only two were functional at that time, Mumbai and Kanpur, but still the separation between the western region and northern region can be clearly seen in this slide here. The green one represents the northern region and the red is the western region. So, the two systems separated, that is what happened that day, and then the NR or the northern region collapsed. Okay, so, the initial separation was initiated by the Gwalior-Bina 765 kV line, but which was being operated at 400 kV, and that trip that can be clearly observed as a notch in the frequency, and then the two systems separated, and then you can see that they are there is a diversion between the two systems, and then there were further trippings of the ER that is the eastern region and the northern region links that can be seen in Gorakhpur, Muzaffarpur, Balia, Patna and Balia, Bihar Sharif. There the ER-NR tie lines tripped, and then ER when I refer to ER I mean eastern region, NR means northern region, WR means western region. That time all the three or in fact north, east, west were one, and northeast were one region. Southern region was not yet connected. It was later connected in 2017-18 in that region when 765 kV Raichur Solapur was commissioned. Okay, so this is, you can see that with a wide area, this is a wide area frequency system, but we will see how a wide area monitoring system will also help. So, you can see that the separation etc. was clearly observed in the WAFMS. This is the western region 400 kV network. The diagram is certainly little old. So, there have been more 400 kV stations that have been commissioned, and also this was during the time of the blackout, and till very recently this was a part of the new grid as was called, north, east and west. Now it is a part of the all India grid. We are one nation, one grid. So, all generators from north, say somewhere near Jammu to deep south near in Tamil Nadu, and from west or somewhere very close to Saurashtra and northeast, they are all part of one grid, they all operate in synchronism. So, but just for the sake of illustration, here it is shown that the western region network is shown with its 400 kV substations, and this these of course there what we want to show here is that there is a SCADA which is located at these substations, but it is slow and it is the data is not synchronized. The SCADA protocols are based upon polling. So, one after other these stations or the RTOs are polled, and this is non-synchronous. So, the delay is somewhere between 1 to 5 seconds or of that order. The order is seconds. Okay, and that is why this assumes that the in that period 1 to 5 seconds there is the power system is in a steady state or at least a quasi steady state. So, the operator, if he is just observing his SCADA data or SCADA screens, will not be aware of any system dynamics which are much faster than this. Okay. So, power swings, we if you remember in one of the lectures we have seen the time duration of each of this. So, power swings are electromechanical oscillations, they are in the range of about 0.5 to 2 hertz, that is the swing frequency. So, with a scanning rate of 1 to 5 hertz, there is no, I am sorry, scanning rate of 1 to 5 seconds, there is no even visibility of the swing, so no monitoring. So there is no, of course, obviously no control action can be taken. Okay, so this is not conducive for any fast control actions that can be taken. So also, as we said, the data is non-synchronized. Okay, so the all the RTUs do not have the same timestamp. They may have a local substation timestamp. So the measurements are time skewed. Also, the fetch time may be of the order of 1 to 4, 1 to 5 seconds. So it is quite slow. And since they are at the central control center, all the time snapshots are not available of the same time instant. So that is why we call it a skew. So the measurements are time skewed. So also because they don't have a common timestamp, each RTU has its own reference phasor, and that is why we cannot correlate one phasor to another. So even though we may have the voltage of two substations, we saw here in the first slide or the second slide, we may not be able to compare the phasors because the reference phasor is not common. Okay, so now to mask it, what was done in the traditional SCADA in terms of the measurements, we just use voltage magnitude, we use P and Q, that is VI star. Okay, so P means we use megawatt and Q means we use MVR. Okay, also we use only the voltage magnitude, not the voltage phasor, that is voltage magnitude and angle, we just use the magnitude. So that is why you got a non-linear state estimator, and then you had convergence problems because you have to have an iterative solution. So all these problems are a result of lack of a common reference phasor and use of local references. Okay, so here we can see that this is just as an example the western region. Of course, now Power Grid has covered all the central substations all over India, and has installed about 1400 or so PMUs, okay, to all over India. So this is under the project URTDCM, Unified Real Time Measurement System. So here this is just to illustrate that there are the PMU placement problem. Earlier there was a lot of literature on PMU placement because it was thought that maybe not all the buses we can install PMUs, though that would be the ideal, and that is what is subsequently done. But there was a period of time, say about 15 years ago to 10 years ago, where people were thinking of optimal placement of PMUs, and then depending on the meshing of the system and the locations, the number of PMUs could be decided. So these were the number of substations that needed to be monitored. This is just again as an example only the western region of India, and this was we had done one such study a long time back where we said that optimal number of PMUs is roughly 1/3 the number of substations to be monitored. Now you may be wondering how a substation can be monitored if there is no PMU at that location and if it is only at a remote location. Actually, I'll just quickly show you how that can be done. As to how the PMU is constructed on that, you just have to hang on for a couple of slides, and then we will come to that. So now assume that we have a 3-bus system, okay, or even a 2-bus system is okay for this example. These are the transmission lines connecting the 3 buses. Okay, so now this is V1, this is a phasor, this is V2, this is the bus numbers 1, 2 and 3, and this is V3, then this is I12 phasor, this is the current I13, this is the current, if there was a PMU here of course, there is I31, I32, I23, I21. Okay. Now, the state estimation problem is defining the voltage phasors at all the buses. Okay. That is what you do in a load flow problem also. But of course, we are not discussing the differences between a state estimation and a load flow, but we need to define this. Now, suppose we have a, ideally if we have PMUs at all the locations, then all the voltage magnitudes and angles get measured by these 3 PMUs. But suppose we have an optimal PMU placement problem, we want to reduce the number of PMUs to the minimum number which can still make the system observable. Okay. So, here what we do is, here if the PMU is placed here at say bus number 1, okay, let us assume that there are no PMUs placed here, then still, and you know the line parameters are Y12, this is Y13 and this is Y say 23. Okay. Or Z for that matter. So, V2 is simply V1 minus I12 Z12, all these are phasors, and V3 is simply, this is known. Okay. Once you have a PMU at this bus, at bus 1, the parameters known are V1, I12 and I13, okay, and V3 is V1 minus I13 Z13, I am sorry, Z. Okay. So, then these 3 V1 is of course measured, V2 is known from this equation 1 and V3 is known from equation 2. Okay. So, the optimal number of PMUs for this is this system is just 1. So, similarly roughly, I mean you need to solve a linear programming problem for this, but similarly you can formulate an optimization problem and get the optimal number of PMUs for any system, like the one we saw in the slide was for the western region, and roughly you get for as a rule of thumb 1/3 the number of with adequate meshing that as is available at 400 kV, you get about 1/3 of the number of PMUs. Having said that, the problem of optimal placement of PMUs is somehow now redundant, because most utilities are choosing to install PMUs at at least all the important buses and important generation buses and so on. So, this problem itself becomes sort of redundant, but it's good to know that such problems were being looked at an earlier date. Okay. So, having said that and having assumed that PMUs are at all locations, now this is how the architecture looks like. Okay. So, this is these are the PMUs at various buses. Now, let us assume that this is an optimal PMU placement that is done, and otherwise there would be PMUs at the center bus here also, and this PMUs are placed at all the buses, and they get their timing pulse from the. So, Yeah, so this is how the architecture looks like. Here you have the PMUs placed at the various buses. They get the timing signal from the GPS satellites. Now we are used to looking at GPS as a locational service or a location service, but here we do not need that because the substations are at a fixed location. But the GPS also provides another important signal, that is the timing signal, that is 1 pulse per second, okay, with an accuracy of nanoseconds. So, all these PMUs, which are essentially like relays in construction, we will see that, and they also have GPS receivers which receive the timing pulse, and then once the PMUs calculate the phasors, then what we do is um, we transmit them to the either the state load dispatch center or regional load dispatch center, as the case may be. And this is, of course, this architecture pertains to India, that is why we have the terminologies like SLDC, RLDC, etc. And then they are assembled, and then whatever analytics have to be run on them or applications have to be run on them are run. Now the synchrophasor measurement transmissions are at the fast rate of 50 phasors per second, okay, so 50 hertz. And the slowest is about 10 hertz, okay. So you can see that in India we are using this is 2 phasors per 1 phasor per 2 cycles, okay. So that is 25 hertz. The standard, that is the IEEE standard, also allows for we will see the rates a bit later, but also allows for 2 phasors every cycle, okay. So 100 hertz for a 50 hertz system and 120 hertz for a 60 hertz system, okay. So you contrast that with SCADA, which is this is 20 milliseconds or 40 milliseconds versus 1 second or 2 seconds of that order, okay. So this is extremely fast, and then you can have you can observe power swings and then take control actions, etc. Accordingly, okay. So this is how the VAM's architecture looks like. This is an outline of the architecture. The actual architecture will look like this. So there are PMUs installed, one PMU or multiple PMUs depending on the number of channels. You get PMUs as basic relays for functioning as PMUs, which can do 2 channels, that is one voltage and one current. So rather it is 6 channels, because you need 3 phases for 1 voltage and 3 phases for 1 current, and then that can go up to 36 channels. So 12 phasors can be monitored, okay. So this is the setup, and the communication backbone is usually fiber optic, because you need a fast very low redundancy kind of communication network, okay. So then that is then taken to a control center, which could be an RLDC, SLDC of that nature, and then you have a server grade equipment which acts as a PDC, that is the phasor data concentrator, and then does the assembly of those synchrophasor data, and then can run analytics on them, okay. So this is already happening. We already have about 1400 PMUs installed in India, and all the PDCs, etc. happening. There are analytics running on the servers. So this is the slowest. If you see, the promise of VAMs is that the synchrophasors, what are synchrophasors? We will see a little later in this lecture, or maybe in the next lecture. Synchrophasors as well as digital information, okay. And digital information means circuit breaker status, isolator status, of that nature, open or closed. Digital, that is, either the circuit breaker can be open or it can be closed, so 0 or 1. It's binary in nature, so it is known as digital information. So synchrophasors as well as digital information will be updated at least every 5 seconds. This is the slowest allowed in the standard, okay. So this is 10 hertz, okay. So of course in India we are using 1 phasor every 2 cycles. So that is 25 hertz, okay. So angle measurements are directly available, okay. You need not mask that and all that, and since there is a common phasor, a common reference phasor, you can directly compare, okay. So so time snapshots of the whole system, because you are getting synchrophasor from all over the system. You can have a time snapshot of the whole system at one location. And latency is because then there is communication latency, whatever is the fiber optic latency or the delay. So that is the latency. We will have a brief look at this latency towards the end of this lecture or the next. And because the swings are of the frequencies of 0.5 to 2 hertz. So, and this is much faster than twice, so it meets the Nyquist criteria also. So, the operator can monitor the oscillations in the system, and then based on that there are some applications which are already developed, some applications which are still in the research domain, some applications are an opportunity for students like you to develop. Okay. So, based on that you can have intelligent control strategies. We can also have also improve emergency control like smart islanding, adaptive islanding, that nature. Okay. Also, not only that, if thus this can prevent the intelligent control can prevent blackouts and all that, but if the intelligent control and smart islanding doesn't prevent any blackout, then the system restoration rather after the incident can also be simplified. Okay. One more advantage is maybe later we will have a quick look at state estimator. Just a very brief look is that unlike a SCADA where we said that you have BI star, so you have P and Q, here you can directly work with phasors, okay, directly work with V and I. So, the state estimator can become linear, and it can be solved in one step, and so there is no problem of iteration and convergence or non-convergence and all the usual problems that are associated with a state estimator or non-linear state estimators. Okay. So, here the very basic, the starting kind of low hanging fruit kind of thing is of VAMs is visualization of system parameters and events. Okay. So, this will enable a higher situational awareness for the control center operators. Okay. So, the PMUs are sending in voltage, current and frequency measurements. Then at the control center you have the PDC or the phasor data concentrator, and then it collects the data, creates a time snapshot of the whole system, and then it feeds it to the applications. You have monitoring, visualization applications where you have visualization, where you have you can visualize the voltage and current phasors. Then you have analytic functions. You also have an archival function, like a historian, where you keep data say for a year or so, then you can analyze it later if you want to do some kind of post-mortem analysis or even any normal kind of analysis. Okay. And then from the analytics you can then as a advanced control function you can have a control and remedial actions. Okay. So, we mentioned situational awareness and or higher situational awareness. So, what do we actually understand as situational awareness? What is the concept of situational awareness? That is obtaining and displaying the information in real time. Okay. So, that this is the perception, what the operator perceives as the state of the system. Okay. So, there are various control centers, various hierarchy of control centers in the power system network. So, effective communication between them at different hierarchies and also peer to peer, that is one part. Then comprehension. So, once having perceived the data or seen the data and perceived the data, what it means to the system. Okay. What is the objective of the operator? What is the voltage range that you want to maintain? What is the flows that are needed to be maintained? All that. So, comprehension, then what does it mean? Is it in the range? Is it out of range, or is it just slightly out of range? Is it in the tolerable range? Is it in the emergency range? Okay. So, and then there will be many parameters which are in the normal range, but certain parameters may be approaching their bounds, or are likely to cross depending on the operator's experience and what the analytics tell him. So then you can the operator can then analyze and narrow down and focus only on the most important decisions and actions to be taken after that. Okay. So projection now, based on what he has comprehended or comprehended the information and perceived the information, and then what the decided course of action is, because you may have certain sets of scenarios that are there, and then based on that and the state of the system, what are the future projections, or what are the what state is the system likely to take in the future. Okay. So all these three combined, perception, comprehension and projection, combined form what is known as situational awareness, and all these things being good indicate good situational awareness. Okay. So the PMU based WAM system indeed helps in good situational awareness for the operators. Now what we will now move on to a little more basic of this is what are phasor measurement units or PMUs. Okay. So these measure phasors with a global reference frame. Okay. That is derived from the timing signal provided by the GPS satellites. Okay. So of course there are other GPS is the American system. We have now PMUs based on our own NAVIC systems also. Okay. That is the Indian ISRO based system. But they are not in commercial operation. They are I mean the research based, and labs have indeed tested it with that. And the communication protocols are all standardized. It is defined in IEEE C37118. Now if you see, this is the block diagram of the PMU. Okay. We have analog inputs from CT and PT, then we have anti-aliasing filters, then we have A to D converters, then we have a microprocessor based brain of the system. So if you see this part, the lower three blocks, they are almost, or rather they are the same as that of a numerical relay. Okay. That is why we take this as an advanced topic in protection itself, that we have covered the basics here in the numerical relaying part. Now what is different is that you have this phase locked oscillator and a GPS receiver, okay, which receives the timing signal. If you remember when we studied the numerical relaying, we mentioned that if the reference signal for all the sample and hold circuits were derived from a common reference, then you could compare phasors across the system also. So this is what it does, that the timing pulse for all the sample and hold circuits is received from the GPS antenna, or from the GPS rather. Okay. So we have been saying, you are rather using the term synchrophasors, okay, in this lecture. Now what is a synchrophasor, and how is it different from a phasor? Essentially it is a phasor with a common reference. Okay. So phasors, or the technique of phasor calculation, has a long history. It was first proposed by Steinmetz in 1893. That this is the reference of the paper here. And this synchrophasor as a term was introduced somewhere in the late 1980s. So it was first referred to, and the first PMU unit was constructed by Professor Fadke in Virginia Tech. And the difference here of course is that the phasor has some arbitrary reference. Okay, it can have any reference. Now one single phasor, if I have some voltage or current, I can place it anywhere in space with respect to with any reference, okay, with any arbitrary reference. So a synchrophasor is however a reference with a standardized absolute reference time. Okay. So this absolute time is the UTC time, and this we will see the how the UTC time is defined. Okay. So as per C37118, this standard, the current standard is undergoing revision. The current standard of course is 2011. The newer standard should have been out by now, but it is undergoing some revisions. The earlier standard was 2005, and then before that in 1997 or so. So, as per the standard, that is IEEE 37118, a complex equivalent of a simple cosine wave such that the modulus is the cosine amplitude and the complex angle is the cosine wave phase angle. Okay. So, this is what we know, the modulus is the amplitude and the angle in the polar form is the phase angle of the phasor. Okay. Now, as far as synchronized phasor or synchro phasor is concerned, phasor calculated from data samples using a standard time signal reference. Okay, this is the UTC time and the standard time reference for measurement. And then because you use a standard time reference, synchronous phasors from any site, from remote sites, can have a common phase relationship. You can relate the phase angles of the two synchro phasors. Okay. So, this phasors and definition of phasors we have seen in when we did the DFT and we referred to phasors, etc. But anyway, we will go through it quickly. So, x of t is xm cos of omega t plus phi, and since omega is considered to be constant, this can be written as xm e raised to j phi Okay. So, since omega t or omega is essentially constant, the problem of determining the phasor essentially boils down to problem of defining xm or xm by root 2 depending on RMS or peak what you, but I mean you should not, and the angle phi. So, these are the quantities that are to be that we need to determine. Okay. Here we say xm by root 2, but even if you write xm angle phi, it is not wrong. You just have to be careful of whether you are referring to the RMS value or not. Okay. This is in the polar form. In the equivalent rectangular form or in the complex number form, it will be x of real plus j x of imaginary. Okay. So, this is how you can equivalently write the two phasors, or rather equivalently write the represent the phasor. Okay. So, now see if you how do you define the phase angle relationship. So, this is depicted in this in this figure here. So, if you have 3 samples, these are 3 x1, x2, x3, these are samples mind you, not the phasors, these are samples derived from measured signal at T1, T2 and T3, these are synchronized with UTC time reference. Okay. So, the cosine is the reference here. So, if you see x1 here, then x1 the angle is taken to be leading, okay, plus phi. Okay. x2 on the other hand is taken to be minus phi. So, as x3 is also minus phi. The range is minus 180 to plus 180. Okay. So, if it goes beyond minus 180, then it becomes plus of the other angle from the other time reference. Okay. So, again just to strengthen our understanding, if you see the first one here is T1, so it is exactly at that cosine 0 reference. So, it will be x is xm by root 2 angle 0. The second one will be it is positive 90 degrees. So, xm by root 2 angle pi by 2. Okay. And the third one as you can see is xm by root 2 angle minus pi by 2. So, the required angle is required to be reported in the range of, sorry, the measured angle is required to be reported in the range of plus minus 180 degrees or plus minus pi. Okay. So, I think this should make it clear whether I mean how the reference is used and how the phasors are reported. Okay, now how is the time tag used? So, the time reference is synchronized with the GPS time. Okay, the timestamp of the full second pulse is obtained from GPS as pulse per second. So, GPS also, as I mentioned, other than the locational information, it also sends the PPS or pulse per second. Each phasor, now as per the standard, the phasor also has to be time tagged with an 8-byte message, with first 4 bytes are the second of century. Now, the second of century is calculated from midnight of 1st of Jan 1970. Okay. So, then the second of century keeps on incrementing. Okay. So, and the next 3 bytes are for fraction of second. Okay. The fraction of second will be or FOS will be divided based on the reporting rate. We will see an example a little later. And then last 1 byte is for quality, whether it is to be taken or totally discarded, or there are ranges like that. Okay. So, the second of century or SOC is a linear count of seconds starting from midnight of 1st of Jan or 1st of January 1970. Okay. Then the leap seconds are added or subtracted as is necessary, or that adjustments are done automatically depending on whether the time has to be adjusted for the leap second. Okay. So, fraction of a second can have, or FOS can have a resolution finer than 1 microseconds. Usually it is in nanoseconds. Okay. So, there are, and that 1 byte means 16 levels of quality indicators from ranging from normal operation to total clock failure. Okay. So, this phasors, there is a frame that is defined in IEEE 37118. If you have access to it, please go and have a look at that standard, which defines the phasor reporting frame, and then the standard requires that these frames are reported at regular intervals. Okay. So, what are those intervals? For a 50 hertz system, it is 10, 25, 50 hertz, and for a 60 hertz system, it is 10, 12, 15, 30 and 60 hertz. Okay. So, there are these different rates are specified in the standard. The standard also specifies that reporting rate can go up to 50. We mentioned 50 and 100 hertz if applicable. 100 means 100 hertz for a 50 hertz system, or 120 hertz for a 60 hertz system if some of the applications require that, but in which case you will have to use a half cycle DFT. Keep in mind, otherwise most PMUs use full cycle DFT. That is not defined in the standard, but we will come to that. Okay. So, as we said, the timestamp of every full second is obtained from the GPS system as a PPS, pulse per second, and then the reporting rate divides the 1 second interval between one PPS and the next PPS into a number of sub intervals. Okay. And that is the fraction of second. Okay. For a 25 hertz reporting rate, you have FOS indicators at every 40 milliseconds. If it was a 50 hertz reporting rate, we would have had FOS, the first FOS at 0.02, that is 20 milliseconds. But since we are talking about 25 hertz rate, you have FOS 0.04, 0.08, 0.12, 0.16 and so on. Okay. So, let us go on to the measurement of phasor. We have done this, we will quickly step through this just as a revision. We have just done it a few classes before in terms of the DFT. Okay. So, this is an if you look at this, it is the I mean it may look different, but it is the same form of the DFT expression, other than the fact that the constant is √2 by n. Okay, that is just done to adjust for the RMS values. If you remember the inverse, we just said that you can have any constant as long as C1 into C2, that the constant for the forward transform and the inverse transform is 1 by n. So, rather the product of the forward and constants for the forward and inverse transforms is 1 by n. Okay. So, here we use the first the first expression here is what we have been used to, or what we have used in the earlier part. The slightly modified version uses, samples from the half the number of samples from an earlier window and then half samples from this window. So, you have k is equal to minus n by 2 to n by 2 minus of 1. Okay. And then accordingly the exponential is also modified. Okay. A phasor with a timestamp of 10 milliseconds will be calculated from evenly spread samples taken at 0.5 milliseconds to 19.5 milliseconds. Okay. So, this is a centered DFT. Okay. So, either either you take it as that half window, or you take the window itself accordingly, or and move the window or slide the window accordingly. Okay. So, what I meant by half earlier window and half this window was the conventional understanding that we had up to this point in the course, but of course, you will not do that. The window itself is adjusted accordingly. Okay. So, timestamp of 10 milliseconds is 20 samples from 0.5 to 19.5 milliseconds. Okay. Earlier what we would have done is this phasor, this would have been the phasor with the samples 0.5 to 19.5 would have been calculated as a 20 millisecond phasor, but here because of the centered DFT it is the 10 millisecond phasor here. Okay. So, here you can see these are the samples that are taken from 0 to 20 milliseconds. The point these are the samples, the plus marks are the samples here. I will just blank this out for better. And so, here you can see that that the peak value is 1, so that the RMS becomes 1 by root 2, and since that is the phase angle. Okay. So, here x here you can see that the peak value is 1, so that the RMS value becomes 1 by root 2, and since it is at the since the cosine will be the reference, the angle also will be 0. Okay. So, the phasor will be reported as 1 by root 2 angle 0. Similarly, just to take a few more examples, here this will be 1 by root 2 angle 0, this will be 1 by, the center one will be 1 by root 2 angle pi by 2 or 90 degrees, and the last phasor here will be reported as 1 by root 2 angle minus 90 degrees or minus pi by 2. Okay. So, while we discuss this as DFT and centralized DFT, centered DFT, the standard does not specify the method of calculation of the phasor. You can use any method, 4 sample method, whatever you feel is the right method. What it does specify is total vector error. Okay. So, the error is specified. Okay. The method of calculation is not specified. As long as you meet this error criteria, you can use, you are free to use any method that you want. So, here you can see that this is the method of calculating the total vector error. The hat shows the measured phasor, and this is the actual value. That is, these are x hat r minus x r, that is the real difference in the real component, and x hat I minus x I is the difference in the imaginary component, and that squared that divided by the squares of magnitudes of each, and then that into 100 will give you the total vector error. Okay. So, here what it says is that the standard 37118 or IEEE C 37118 specifies the most stringent level is 1% TVE under the steady state condition of plus minus 5% off nominal frequency, 10% total harmonic distortion, and 10% out of band interference signal. Okay, so 10% total harmonic dissonance, 10% out of band, whatever is the band, we will see what that is. And then under these conditions it should meet 1% TV. If you see here in the small diagram here, the small circle, this is the phasor, okay, the actual phasor, okay, and if the TV is 1%, then it can lie anywhere in the small circle that you can see, okay, and if the TV is 10%, then it can lie anywhere within the large circle that you see. Okay, so this is the level of accuracy that what TV is equal to 1, total vector error is equal to 1%, is the level of accuracy that is specified in the IEEE 37118 or the synchrophasor standard. Okay. Again I repeat, if you have access to this standard in your colleges or in institutions or wherever if you are working, please go and have a look. It will clarify a lot of concepts. Okay, so now what can the PMUs do? The PMUs can here PMUs can observe the low frequency swings. Okay, so the power swing the power view. If you remember the lecture on distance relays and effect of distance power swings on distance relays, we discussed power swings in some detail. We saw the mathematical modeling also, and then how it appears on the RX plane. That is not the RX plane is not important here. If you just try to recollect the power swing from that those lectures, the range is 0.22. I am sorry, here it is mentioned 0.2, but it is usually the range of 0.5 to 2 hertz. And then from the we have seen the Nyquist criteria, and then to observe such swings, the reporting rate should be greater than twice this. So, it should be greater than 4 hertz, and the lowest that the standard allows is 10 hertz. So, this can be comfortably observed. Okay. So, here if there is also we saw some aliasing effects and all that in the initial parts when we saw the Nyquist criteria. Okay. So, here if there is an interfering signal of 9 hertz, it will be aliased as a 1 hertz signal. This can be seen as an erroneous swing. So, we will need to have a cutoff at say 5 hertz or 6 hertz. So, that has to be the anti-aliasing filters have to be properly designed. Okay. So, standard specifies that with such an interfering signal of 10% magnitude, the TV shall be still below 1%. So, you have to adjust the filtering requirements accordingly. Okay. So, the 1 hertz signal could be a real swing, and it has to be measured because it lies in that range of 0.5 to 2 hertz. The 9 hertz swing signal would be an interfering signal, and it needs to be cut off or attenuated. Okay. So, what we do, we need an anti-aliasing filter or a low pass filter with a cutoff frequency about 5-6 hertz. Okay. And so, this is required to meet the accuracy requirements in the presence of out of band signals. Okay. And then this will also, as we saw, low pass filter usually is a stack of RC elements. So, then it will slow the response time and it will be of the order of 150 milliseconds. Okay. So, we will stop this here and then continue in the next class with response time and reporting latency and other aspects of PDC and applications. Okay. Thank you.